Yeah.
Hello everyone, thank you for attending today's ISR IAA colloquium. Our speaker is Dr. Mathieu Aubailly. His talk is Adaptive Optics Imaging Through Deep Atmospheric Turbulence. Dr. Aubailly received his PhD from Michigan Technological University in electrical engineering in 2005. His work at Michigan consisted in the development of reconstruction methods for adaptive optics imaging. Developed techniques were tested and validated on experimental data from the USF 3.6 meter AEOS telescope facility on Mount Aliaka, Maui, Hawaii. Dr. Aubailly's research interest lies in the analysis, development, and experimentation of imaging systems operating under turbulent conditions. He has extensive expertise and experience in turbulence effect mitigation by image fusion with applications to short to medium range near ground imaging conducted at the Army Research Lab in Adelphi, Maryland, and at the Sandia National Laboratories in Albuquerque, New Mexico. His area of expertise also includes high dynamic range imaging and modeling of holography-based imaging systems. Prior to his current position, Mathieu worked as a research associate at the Intelligent Optics Laboratory. He conducted numerical analysis and development of imaging networks of adaptive sub-apertures. Please welcome Dr. Aubailly.
Thank you. Hi everyone, and thank you for coming. So the Intelligent Optics Lab is part of the ISR. It had been in the ISR for a number of years, but so far we have not been collaborating much with the faculty on campus. We had been working mostly with our sponsor, the ARL. And we want to change that, and Reza Godzi mentioned that this seminar will be a good opportunity to let the department and the rest of the faculty know about what we do and how we could collaborate and hopefully write a joint proposal and so on. And so why do we have adaptive optics on campus in the ISR? Adaptive optics systems are pretty interesting systems. They involve optical and mechanical components. They involve real-time control to compensate in real time the random media effects that random media can have on our systems. They involve sensing, so either like we measure an image, directly an image, we can measure the phase of the optical wave that we receive, phase aberrations. And also it can involve image processing or for noise mitigation or such things. So the system that you see here is kind of a stereotypical adaptive optics system used in astronomy. So the light that we receive from our object gets corrupted by atmospheric turbulence. We use a deformable mirror which compensate the aberration introduced by the atmosphere, and we sense the residual error which is used to feed the loop, the feedback loop. And in parallel to that, we monitor the image before and after optimization. And there are other applications than in astronomy. So historically, adaptive optics come from an astronomy, but it had been applied also to the field of to the medical field, especially with retinal imaging. For example, here you see an image of the cones on your retina before and after adaptive optics compensation. Adaptive optics also used to diagnose high-order aberration of the eye, and it can be very useful for LASIK surgery prior performing LASIK surgery. In laser communication, adaptive optics is also used for remote imaging as well, for defense application. You image several kilometers away, so it can be a very convenient laser beam propagation for laser weapon. In microscopy, also adaptive optics is used. Also, to monitor the quality of optical elements that you fabricate, adaptive optics techniques can be used. So what do we call deep turbulence? So we define deep turbulence mostly in contrast with astronomy scenario. So in astronomy, we are usually looking up through a rather thin layer of turbulence, because most of the propagation is in vacuum, and only when the light reaches the atmosphere it gets corrupted. And the telescopes, ground-based telescopes, are usually very in rather high altitude. So as a result, the turbulence are rather weak. So it's a good. These are good conditions to compensate almost fully the aberration introduced by the atmosphere. And as a result, in astronomy, they get very good image quality. And so typically the quality that is obtained with your astronomical telescopes is related not so much to the atmospheric turbulence, but related to the size of the telescope. So the larger the telescope, the better the quality. That's why we keep on building larger and larger telescope. In deep turbulence, the deep turbulence conditions are pretty much the opposite. Usually we are looking near horizontal, almost horizontally. The turbulence is distributed all along the line of sight, so the turbulence is not only near your receiver. We're also usually at lower altitudes, so the turbulence is typically very strong. And currently there are not, the quality of the performance of adaptive optics in deep turbulence is nowhere near what they achieve in astronomy. In astronomy, they get compensation ratio of 80-90%, almost perfect correction, whereas in deep turbulence, if we get like 30 or 40% efficiency, we are very happy, and it doesn't happen very rarely. Yeah, very often. So what happens if we apply conventional adaptive optics techniques to in a deep turbulence scenario? Well, we have two problems. The first issue is which we call anisoplanatism, is related to the fact that the light in our receiver, the light that comes from one part of your object doesn't go through the same, doesn't experience the same turbulences than the light coming from another part of your object. As a result, if your adaptive optics use that part of your object as a reference, the light coming from that one will not be properly compensated. The image here that you see on the right is the image of it's an array of point sources. So you can imagine an array, a grid of point sources, let's say maybe 10 centimeters apart, and you look at this object about, let's say, 2 kilometers away. And this is the image that you will get from that object, where if that spot is used by your adaptive optics system as a reference, it will correct properly that spot. But as you go away from your reference beacon, the compensation realized by the adaptive optics is completely inefficient. And as a matter of fact, if you go too far off your reference beacon, adaptive optics degrades even the quality of the image. So that's the first issue we have with conventional AO. The second one is related to the, it's a different problem. If imagine that you have an optical wave that propagates through atmospheric turbulence, and a uniform optical wave. If you look at astronomical scenario, the light that you will receive in the aperture of your telescope will remain almost uniform. On the other hand, if you propagate the same optical wave horizontally, it will experience strong fluctuation of the intensity. So if, let's say, if you have a small telescope that is located here in one of those very dim areas, you are out of luck and you will have very bad measurements. So that's one of the problems that we experience in deep turbulence. In addition to that, when in those very dim areas, as your optical wave propagates through the atmosphere, the phase of your wave will experience some discontinuities. Some phase discontinuities will appear slowly as you propagate, and so here, as you can see, here the phase gets somehow teared apart in those two locations, and as you can imagine, if you try to compensate this dislocation, phase dislocation, using a continuous deformable mirror or some other kind of continuous correction device, you're not going to get a very good correction. So about the first issue I just introduced, astronomers came up with a solution to mitigate the effect of anisoplanatism and correct imagery over a larger field of view. So so here we have a telescope, we have our object, the object we are looking at, and in astronomic situation you have turbulence layers that are reasonably well defined and rather thin, so that you can use multiple mirrors. Each of those mirrors is being conjugated to a specific layer and will compensate only that layers. And if those mirrors are well controlled enough, you will be able to compensate each of those layers and increase the quality of your imagery over the entire field of view. So this technique had been proven to work pretty well in astronomy. However, it requires different measurement of the wavefront in different planes, and but unfortunately the wavefront sensors that are used to measure these aberrations do not perform very well at all in deep turbulence. And so as a result, it's this conventional type of multi-conjugate adaptive optics does not work well in deep turbulence. So we came up with a different scheme to compensating atmospheric turbulence, deep atmospheric turbulence. So it's that part. So it's represented here. So let's say we have an object that we are trying to image with our system here. We have distributed turbulence all along the path. And what we do is that we use a bunch of deformable mirrors. Each of those deformable mirrors is conjugated to a slice of the atmosphere along the path. And each of those mirrors is dedicated to compensate only that small part, that small section of the atmosphere. Finally, we look at the image that we, after those different layers of correction, and we use this image, we do some image analysis to close the control loop and control each of those mirrors. So how can we differentiate the effect of the different layers on our image? Well, there is an interesting, it's a property about this type of propagation, is that the different layers along the path do not have the same effect on the final image. So this is illustrated here. So those three images are an image of a target that is about 50 centimeters large over a 2 kilometer horizontal path. So this is the type of image that you will get if the turbulence is concentrated near your receiver. So as you can see, the image aberration correspond mostly to geometrical distortions. On the other hand, if your turbulence is concentrated next to your target, next to the object you are trying to image, the image aberration will mostly consist in a blurring effect. So by analyzing this image, you can somehow get information about about the distribution of your turbulence along the line of sight. And you can, and from your image, you can derive different metric corresponding to the different layers, and you optimize those metric to optimize your image. And you do that in parallel for all the deformable mirrors until you get a good image. And I should mention that this work is being mostly undertaken by my colleague Marie Igouf, who joined us about 6 months ago. She comes from a laboratory in France that is specialized in, there's the main laboratory in France that's specialized in adaptive optics. So, and they have a very good knowledge of multi-conjugate adaptive optics, and so that's why I was glad that she would join us for a while at the ISR. While Mary is doing some numerical simulation to develop further this type of system, we performed some preliminary experiment at the ARL. So here is an overview of the test bed that we have at ARL. We have an optical we have a line of sight of about 2 kilometers going from a water tower, on top of which we have different antennas and laser sources, and our laboratory, and we have some kind of a periscope system that allows us to access this beam onto an optical bench, so we can set the adaptive optics system indoor. So once we receive the beam from the optical path, we have this is the optical schematic of what the beam undertakes. So we have different. Here we have a set of mirror for alignment mostly, and more interestingly, we have we have 3 adaptive optics systems in this setup. We have 2 deformable mirrors and 1 tip tilt mirror. So the tip tilt mirror corrects for the shaking of the image, whereas the deformable mirrors compensate for higher order aberrations. And so when I mention deformable mirror, I should explain a little bit what we mean by that. So here is a picture of this typical devices. These are developed by the Army Research Labs in Adelphi, not so far from here. And there are devices. This one is about 30 millimeters across, and they are divided into a small piezoceramic pixels. And under each pixels, you have the electrodes. And by applying a voltage, you can deform each of those pixels. And in the end, you have a different control. You can control independently all those pixels. Here is an illustration of the response of those mirrors. To give you an idea, so this 30 millimeter mirror, you can manage to focus a beam at a bit less than 4 meters away. So that gives you an idea of the focusing power of this small device. And also one key property of this device is that it can operate at several kilohertz. So that's actually kind of a key point. So it can compensate atmospheric turbulence in real time. So a few words about how do we control this adaptive optics mirrors. So so we measure an image. As I said earlier, using a rather fast camera, we get an image of the object we want to look at. From that image, we derive an image quality criteria. So the higher the number, the sharper your image will be. If your image is very blurry, it will give you a low number. We feed this information. It's a single number scalar information, and we feed that to an optimizer. It could be, the optimizer could be based on different type of optimization algorithm. We can discuss different implementations later, and the optimizer will optimize the commands that are sent to the different deformable mirror in order to optimize this metric. In a sense, it's a very simple system. So and it will iteratively send commands at a rate of a couple kilohertz, so that it always maximize our quality metric. So here is a small video of the top of the water tower image over the 2.3 kilometer path with the adaptive optics system that I showed you. So here the system is off. It will, right now we just turned it on when it becomes green. It's slightly sharper. Here we're back to off, where it's definitely more blurry, and we turn it back on again. So this is to illustrate with a preliminary experiment that there is some hope in correcting wide field of view images using adaptive optics without any wavefront sensor. We just optimize an image quality metrics, and there is no other sensor. To give you an idea of the value of the image quality metric when the AO system is on, about doubles compared to when the AO system is off.
Could we just look at that clip one more time?
I have a quick question. So you mentioned you have several deformable mirrors.
Yeah.
How do you determine, like, when you run optimization, do you run them individually, or how do you determine?
So in the current situation, it's all in parallel.
Okay.
So from the optimization engine point of view, they're all the same.
Okay.
You have 2 times 31 channel, and it sends voltage to keep the metric up.
And that metric is based on?
Image sharpness. It's a typical, yeah. There are probably, it's an interesting field of study, like to determine which image quality metrics work best.
So there's no assumed model for the assumption for the turbulence.
In that preliminary experiment, there is not. But we definitely the control scheme could definitely be improved if we include turbulence strength, turbulence profile, maybe a better model of the deformable mirror geometry. Yeah.
Matthew, how many realizations of the deformable mirror do you perform each cycle in trying to correct the image? Because the turbulence is running up to hundreds of hertz.
Yes. So to give you an idea, the deformable mirror has a bandwidth, this particular DM, over 10 kilohertz. So it can update at that speed.
So several correction cycles per
And
few milliseconds, right?
so when you turn on the system and you go from no correction to convergence, it takes almost between 50 and 100 iterations of the algorithm to converge. However, once you the atmospheric turbulence do not change that fast. So once you reach convergence, then it's very small work for the DM to track, to keep up with the turbulence. So yeah, that's why we have an interest in compensating as fast as we can, because then we have to move very little from one cycle to the next. So that was the approach that I showed you was very hardware based, where we had real-time DMs compensating for turbulence. But recently we came up with a radically different approach, which we refer as digital adaptive optics. And in that approach, we get rid of the deformable mirror and wavefront sensor hardware devices. And what we do is that we mimic that compensation loop in software. In order to do that, you cannot simply measure an image of you cannot only measure an image of your objects. So what we do is that we measure we get a full measurement of the optical wave. By full measurement, I mean we measure the intensity distribution of the light that we receive in our telescope aperture, as well as the light. So from this complex field, then we have all the information that we need to form an image, and you can also compensate for wavefront aberration and so on in the digitally. So which we do as a post-processing step. But this is only possible if we have a good measurement and also a high measurement resolution of the full optical wave. So this sounds like a pretty attractive techniques in the sense that it gives you a lot of flexibility on the software side. You can imagine having a deformable mirror with essentially infinite dynamic range or extremely fine resolution. But this is only possible if you have a good measurement of your complex field. So and also, yeah. So what type of sensor do we have exist to measure the complex field? Well, the most challenging part is to measure the phase of the optical wave. So if we use the most commonly used wavefront sensor in adaptive optics is called the Shack-Hartmann sensor. And it works as follows. We have Shack-Hartmann sensor is pretty simple design. It has an array of small lenses, and we place a camera in the focal plane of those lenses. And your optical wave that falls onto your sensor will produce a small spot behind each lenslet. And if your wave arrives at a small angle on your lens, it will displace the focal spot in the focal plane. And from the spot displacement, we know the slope of the wave that was falling onto your sensor, and we measure the slope for each of the small spots in the focal plane, and from this information we can reconstruct the phase in the pupil plane of your telescope. This sensor had been, is by far the most commonly used, and it works quite well in astronomical situations, because the light that we receive in the pupil plane is in our aperture of our telescope is rather uniform. However, if you use a Shack-Hartmann sensor in a deep turbulence, this is a typical measurement that you will get in the focal plane. So this was taken using a 90 centimeter telescope over near horizontal path. I believe it was looking at it was a star. So this is a real yeah, it was a yeah. So the problem you can see on this small video is that in those areas that are very dim, you will have very poor signal-to-noise ratio to estimate the local slope. And if you use this information to reconstruct the phase, you will have a very inaccurate data. So conclusion is that Shack-Hartmann wavefront sensor is pretty much useless in deep turbulence. So we need to come up with different scheme for measuring the phase. Another approach is it's a family of sensors that are called phase diversity sensor. So if you have like an optical wave entering your sensor, you can split that wave into two legs. You measure you get a first measurement of the intensity distribution, and then you can use a lens and place a second camera in the focal plane of the lens to get an idea of your spot. So those two measurements essentially contain the same information, except that they are not taken in the same plane. They both encode information about the phase aberrations, and then through signal processing you can jointly process those two images to reconstruct the phase. But the inconvenience of this type of sensor is that it requires a very high dynamic range camera. So in those dim areas you have a lot of information which is pretty hard to recover if you do not want to saturate the central spot of this in that case. And so so unfortunately this type of sensor is not very suited for deep turbulence deep turbulence conditions. So we need a new type of sensor, and we designed a new sensor that combines the advantages of both of those sensors. So it combines the high resolution output of the phase diversity sensor, and it's also based on the same lenslet organization than the Shack-Hartmann, except that we use larger lenses, so we encapsulate more light, so you are more resistant to intensity fluctuations. And compared to that sensor, we reconstruct over a smaller subsection of the image, so it reaches a convergence much faster than in that sensor scheme. Here I have a few slides about how we perform phase reconstruction with those sensors, but if you want more information, we can discuss it later. This slide is to illustrate how does the new MAPR sensor behaves as turbulence strength increases. And so in red we have the MAPR convergence curve. Here we have a scale of the turbulence strength, and compared to a classical sensor, it behaves much more robustly as the turbulence strength increases. Well, let's keep that. so far we have been mostly we have been performing numerical analysis of for digital adaptive optics based using the MAPR sensor, and it looks very promising. So we can so now that we have a sensor that can provide us a high resolution full measurement of the optical wave, what do we do with those measurements? Using digital image processing, we take the output of the MAPR sensor, essentially phase and intensity distributions, and we this block essentially mimic a digital an adaptive optics systems in a digital manner. So we have a wavefront compensation section, then we form an image, we pass a lens in numerical simulation, then we propagate the light behind that lens, form an image, and measure the quality of that image and optimize the image until we have a good quality image. Here are a few numerical simulation results of this of the digital adaptive optics system. So on weak turbulence, before correction and after corrections, this is of a rather strong turbulence over it was over 2 kilometer path. To give you an idea, this object is about 50 centimeters across, and we were glad to observe some decent image quality improvement using that approach, and using in that case there is no mechanical elements, there is only a single complex field sensor. So we're pretty glad about that. Here is a third approach for performing imaging in deep turbulence. It's not considered as adaptive optics, it's purely image processing, but nevertheless I thought it would be interesting to mention it in this seminar. When you image an object for atmospheric turbulence, atmospheric turbulence is a random media that introduces randomly good and bad effects onto your images, and from time to time, on occasion, parts of your images will provide a sharp small section of your image, while the rest of the image might be blurry. And if you take a series of short exposure images, amongst all those images there will be some good sections. So if you pick up all the good sections of a series of images, couple hundred let's say, and fuse them into a single image, you can eventually, if you wait long enough, obtain a better quality image. Here is a small illustration of that approach applied to, I believe those were near ground images obtained through 250 meters, I believe, at the ARL. So on the left you have before correction, on the right after correction. You have a few artifacts that appear here and there that are due to imperfection in the fusion, but overall it gives you a significantly slightly better image quality. Here is another object. So in green you have the image quality metric for the fused image, whereas in red you have the uncompensated image, and your image quality always remained above the uncompensated image. Here are a few more examples when we try to mitigate noise using different filtering techniques. And once noise is mitigated and image stabilized, we can fuse images. So here you see a little, those are antennas imaged about 1 kilometer away horizontally. So you have definitely better imagery here than here or there.
Matthew, how well could you do if you took many frames of the fluctuating image and then for each small region average over those many frames to come up with a local point spread function and then use that to deconvolve an average of the image at each point? Is that sort of what you're doing in a way?
Yes and no. Okay. What we do is we wait until the atmosphere is cooperative enough so we have a very good small section. But there are other approaches that do deconvolution and also dewarping. Some other people try to compensate those atmospheric geometric distortions. This approach, in a sense, is very simple. It's very light to implement compared to those. But indeed, yeah, deconvolution would be a good thing as well. So the atmosphere affects differently different wavelengths. So if you process a color image, it's beneficial to process individually each channel through a different Lagrangian fusion pipeline. And so the adaptive the parameters of the algorithm will be slightly different for the different channels. So when you do a Lagrangian fusion, also you can also, I'm sure some of you are familiar with high dynamic range imaging. It's used a lot in digital photography or even analog photography. So you take differently exposed images, a typically exposed image. Here is an image that is completely overexposed, but it has the advantage of bringing up these previously dim areas. And so the same algorithm can fuse those two images into a very contrasty image. So it has so that the same algorithm can fuse differently exposed images as well as compensate for atmospheric turbulence aberrations. So it has the advantage of being very quite simple to implement. And so there are different. There are a number of topics that could be further developed in our work on the image processing side, of course. As you were mentioning earlier, the control loop could integrate more. We definitely could improve it by integrating more information about the atmospheric turbulence, the strength of the turbulence, the profile of the turbulence, if we manage to measure it. The algorithm, the control scheme also would benefit from knowing more, getting more information about the hardware. As you probably have noticed, in the deformable mirror, each pixel doesn't have the same shape, and each pixel, as a result, doesn't have the same influence on the resulting image. But in the current implementation of the controller doesn't make any difference between any pixel of the mirror or between any mirror. So we should include more information, a better model of the optical schematic into the control algorithm. Different image quality metrics also could be used, especially image quality metrics that reflect better the human perception, because it doesn't always match. You show two images to a user, and their perception of a good image will commonly often contradict the metric that you would compute from those images. So that we could pay more attention. Also, one of the goal of this seminar was to let people know what we are working on and potentially collaborate on joint proposal And maybe also some of you are from different fields and might find benefits in applying these techniques to the medical field or other fields, because it's, in a sense, it's a bit frustrating to use all this technology and techniques to only to a very small field. So far, we applied it only to the imaging for defense applications. And thank you very much.
How do you handle getting absolute phase if you've had multiple 2π phase rollovers?
Well, there are unwrapping techniques that can be
I suppose in sharpening up the image, you're sort of doing that, aren't you?
So, well, the phase wrapping is only a mathematical representation. The mirror can handle many doesn't care, but
the mirror can handle it. But how do you know how much phase shift to put on the mirror based on your phase measurement, unless you know the absolute phase?
Well, currently we have no phase measurement in that approach. There is no wavefront sensor. We purely optimize image quality. In a sense, much simpler.
Any other?
Could you explain phase diversity sensor once more, please?
Okay. Yeah, I didn't put details about the. So let's say we have measurements of the intensity distribution in the pupil plane and in the focal plane. So we pick up those two. We have those two measurements. There are a number of algorithms that can reconstruct phase from those two intensity measurements. For that problem, the one that we found to work quite well is called Gerber-Saxton, and it's very simple. You start from an arbitrary. You compose a field, a complex field with an arbitrary phase, and this measurement of the intensity distribution. You propagate it to the focal, numerically to the focal plane of your system, and you replace the intensity with that measurement. Propagate it back to the pupil plane, replace with that intensity. And you repeat that cycle until convergence. And it will reconstruct the phase. As an output, you will have the same phase and you had is the input. It's quite simple, in fact, but it works quite well.
Now, in the labs that you had with multiple deformable mirrors, is there an optimized distance between the deformable mirrors or like even the other optical components, like a physical replacement distance?
So you mean so that your mirror will be conjugated to a plane along the line of sight, or?
Yeah, so that each deformable mirror can, I guess, make the most correction.
So the layers close to your receiver will have the most impact on your image. So in general, if you have a single deformable mirror, put it in the receiver plane. Don't put it close to your camera, or put it as close as you can as the pupil plane of your receiver. If you have two mirrors, then it's another problem. Then you have a benefit in placing the second mirror not too close from the object, because then you have no impact on your image. But I would say, yeah, a little bit off the pupil plane for the second mirror. But Mary is actually working on that through numerical simulations. She's figuring a bunch of things. Sorry.
Thank you. Is there a digitizer somewhere in the system? Where does it fit? And what volumes of data result from a system like this?
So in collaboration with other colleagues, we're building such a sensor. And to give you an idea, so this is a 256 by 256 sensor, 16-bit data. It takes about 30 to 50 iterations of this algorithm to reconstruct a single small section of the phase. So currently, this type of sensor, this high-resolution complex field sensor, still doesn't work in real time. So we measure those data, and then we reconstruct the complex field, and then do image formation digitally. We do not, in that approach, it's not done in real time. While for the approach one that I showed, the deformable mirror-based, hardware-based technique, that was in real time. There is no choice. We need to compensate the atmospheric in real time. But for that second option, since we compensate aberrations in post-processing, we have all the time in the world to process the data.
So what kind of processors are you using, and how long does it take?
We use GPUs to reconstruct this. It takes maybe, it works at maybe 10 Hertz or something like that.
10?
10 Hertz.
In terms of time, how long is it taking?
So this type of sensor produces this type of a new phase, if you want a fully reconstructed phase, every 100 milliseconds, roughly. It's a FFT-based algorithm, so it's reasonably heavy in a sense. Yeah.
So any other questions for our speaker? So let's thank our speaker one more time.
Thank you.